said, no cheat stolen from the internet. Clear, concise, I think, and gets to the point. The very first thing I did with my fourth hour was, hey, it's not that those are wrong, but I am never going to accept that notation, and we need to change that notation. And I'll do one of them up in the corner there. And then in here, I was working with someone here. This means whenever the degree is even and the leading coefficient is positive. So this happens if your degree is x to the fourth, x to the sixth, ECT, et cetera, et cetera, et cetera. We should know that the end behavior is these arrows end up and up, just like a quadratic with a positive leading coefficient, right? Okay, so we remember that, and that should be pretty easy. Same thing with this. If it's a negative leading coefficient and the degree is even. Who's just walking in here? What's going on? We were just talking about you. All right, comes when she wants. All right, you got to pass from your English teacher again, or what? No, well, you always complain when we go to the bathroom. I do. I'm going to complain again. Okay, here we go. Here, I got my complaining done. All right, and then so on and so forth. Hopefully you know x cubed, x to the fifth, and x to the seventh, and so on and so forth. And then negative x fifth and x7, and so on and so on, and ECT, et cetera, et cetera, et cetera. Okay, so let's move this over here to circumvent and speed this up. What am I looking for in these boxes? We've already done this. Oh, I love when you say that, Mr. Samuelis. Thank you. You will write this in limit notation. So this says, what does y approach? Or what is the limit of y? But that's what a limit means, approaching. So what does y approach as x approaches infinity? And this is how we're going to write it. And then that first box, it's infinity. So as x approaches infinity, so does y. But you're going to write it like that, not like this. And if you do, you're gone because you don't follow directions. All right, and that's how the world works. Limit of f of x as x approaches negative infinity. In that first box, that is also infinity. That means, the arrows end up and up like this. So I really like how this worksheet does certain things, most of it. Some things I will cancel out, or it's not that this is wrong. It's just we need to get the limit notation down. All right, this is definitely a way that books write this, and it's okay. Steps for graphing polynomials. We're not really going to go into this too much. We probably will do step 1 and 2, but then we're just going to make a sketch. I'm not even going to ask you to do table values. Not even going to do that, but you are going to have to sketch the graph by understanding what the end behavior should be because of the degree of the polynomial and the leading coefficient, what that means for how the graph finishes off. Okay, so again, just to reiterate, I did this first box, but I wrote it in the correct notation. I could go to all those other boxes and change that notation. I don't have space. I think the point is made. But looking at the negative x to the third graph real quick, as x goes to infinity, y goes to negative infinity. As x goes to negative infinity, y goes to positive infinity. So it is good reading here, but you will write it in limit notation, and that's how the notes will look here on out. And I did a lot of extrapolating with this. I don't want this video to be long. Because of my 7th hour, I don't want to overload them with something extra tonight. But they are going to be expected to look at this. Some people already picked up the notes from 7th hour. And I don't have a 6th, which is good. That won't be interrupted. But just look at this and what this says. Clear? And we'll use our calculator. Let's just go ahead and do... This is what's coming up, by the way. This is page 3. But let's put like x minus 3. Close it. And then put in x plus 2. Here's your future. Your future looks bright. What is the 0 for x minus 3? Meaning when I plug this number in, it makes that set of parentheses 0. What is that number, everybody? 3, 2, 1, go. 3. What's the 0 for the second one? 3, 2, 1, go. Those are also the what for the graph? X-Intercepts. So I know you know that. And then we can look at this. By the way, this is a parabola. I should have went a little bit bigger than that. Okay, but there's a parabola. We already done parabolas. That's intercept form of a parabola, even though I didn't really talk about that. We did vertex form. Well, now watch this. You want to get nuts? Let's get nuts. Let's add to the x plus 2 a squared. So squared. Now, first of all, this is page 3 as well. I'm going to ask you this question. What does this turn into? Is it an x squared, an x cubed, or an x to the 4th, or an x to the 5th? One of those three. 3, 2, 1, go. Oh, nobody knows. Just think about FOILing. If I were to FOIL this out, what would be the leading coefficient or the leading term here? 3, 2, 1, go. Cubed. We should see that. So I'm going to do this. Here I am on the screen. I shouldn't move so much because the microphone isn't the best. What is it going to be? Is the graph going to look like this, this? I'm looking at myself at the camera. This or this? A, B, C, or D? A? Yes or no? It's going to look like this when we're done if it's a positive x cubed. Is this yes or no? That's a yes. Okay, looking at me, it's going to end like this and end like this on the right side. So as x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to negative infinity. And that's what's coming up here. But let's look at the graph. Watch. Oh, this is a special situation. Look at what happened at -2 now. What would you describe that graph? What did it do? And the math word is tangent. It's actually tangent to the x-axis. But really what it is, or a nice simpler word, is it bounces there and stays below. So that's what this little section here is. And we'll just do this quick extrapolation. And then you want to get crazy? Let's go crazy over here and go to the x plus 3 and put a cubic on it. So second insert, carrots, delicious, and then 3. Now what is that going to end up being? An x to the what? So now think about FOILing. If I had x minus 3 times, fumble and fumble, what's x times x times x? X to the, say it, third. And then if I had x plus 2 times x plus 2, I'd end up with an x squared. What's x to the 3rd times x to the 2nd? X to the 5th. These are all basic things I'm asking here. You have to be able to visualize that this is what would happen. Okay, so here we go. A, B, C, or D? A, B, C, or D? Which one is it? Fumble. What letter? 3, 2, 1, go. What's an x to the 5th look like? It goes up here. This is stuff we did last year. What kind of degree is it, everybody? Odd or even? This stupid computer. I can't scroll up here. There we go. Is it even or odd degree? Which one is it? Even or odd? Odd. Is it positive or negative leading coefficient? Positive. So how does it end? A, right? That's what we got to get from what we had last year, and we got to get it fast. Okay, but what I'm really identifying is watch this. Oh no. And my loops get real high because once we put those major degrees in here, it gets steeper and steeper on the loops. We still have the bouncer. That's for x plus 2 squared. Notice at 3 positive now, this graph looks cubic as it goes through. Cubic function, our cubic family of functions. It goes like this when it goes through like this, and then squigglies, and then does that. That's only if you got your family of functions down from our previous chapter. But that's what we need to really know about that, and actually on the quiz make that little squiggly happen. All right, so in this section, that's what this says. When your 0 has odd multiplicity, ooh, all right, I'm going to really hammer this down on page 3 or 4 whenever it comes into play. Odd multiplicity is also just raised to the 1st power. But notice to the 3rd power, the graph still went through. All right, so to the 1st power, it just goes straight through. 3rd power, 5th power, 7th power zeros, they actually have that little cubic shape going through. But then for squared, 4th power, 6th power, but I don't think we'll get that bad. The graph bounces and then stays on the same side of the x-axis depending on which direction it's coming from. So that's what this all says right here, and I like that on the first page. It really condenses what you need to remember from last year or 2 years ago. I'm sure this was last year. Polynomials are huge with the my program got mad that I went to another program and it's throwing a fit. I should call on people. But here we go. What's the degree of the first one? 3, 2, 1, go. 7. What's the leading coefficient? 3, 2, 1, go. 4. So now this is going to go fast. Leading coefficient is 4. I don't know why that changed that. And because the degree is 7. Now, graph comparison. I think it's asking, is it more like the x squared or is it more like the x cubed? Which one is it? Is it more like the squared or the cubed? Cubed. And it's the positive cubed. But what I did have is somebody do this, and this is actually true. Possibly 1 turn, 2 turns, 3, 4, 5, 6 turns, 7 directions. That's possible, like a roller coaster. So I want to reference something else that I liked about this sheet. It's up on this page. Maximum number of turning points, which actually represents extrema. Minimums and maximums. I like that. The one that we have here is a degree 7. 7 minus 1 is 6. The maximum amount of extrema could be 6. 1, 2, 3, 4, 5, 6. All right? Because that gives us 7 different directions. Increasing, decreasing, increasing, decreasing, increase, decrease, increase. Irregardless, look at the end behavior. As x goes to infinity, what does y do? What's the answer to this? In 3, 2, 1, go. Infinity. All right, x finger, y finger. And then as x goes to infinity, negative, where does y go? 3, 2, 1, go. In this case, it's negative infinity because as I go left for x, y goes down. That's how we have to look at that, right, on that second one. And that's how we're going to write it, or else you're gone. I better have LIM in there. All right, next one. So I like this. Now it's all fast here. What's the degree? I want that first. 3, 2, 1, go. 6. Okay, what's the leading coefficient, unfortunately? Negative 7. So if it's degree 6, potentially, it could be less. But the maximum amount of terms could be 5, and it has to end down. I think I did 5 turns there. 1, 2, 3, 4, 5. Maximum amount of extrema would be 5. It could be less than that. But it's definitely going to end down and down because you have a negative leading coefficient on an even degree. So really what this person was asking is this most mirrors a negative x to the second, an even degree here. So the limit of f of x as x approaches infinity, negative infinity. As the x's get larger, the y's go infinitely down. That's those arrows tell me the x finger, y finger action. Right? And then same thing with as x goes to negative infinity. As x goes to negative infinity, notice I am wording it like the boxes, but you will write it in limit notation because it does say the same thing. Limits means approaching. So what is y approaching? All right, what's the last one? What degree is it? 3, 2, 1, go. 5. What's leading coefficient? Negative 2. And then I always do this. Is it A, B? Actually, I think I'm flipped on the camera, so you may not be able to look at it that way. But A, B, C, or D? 3, 2, 1, go. B. I heard a couple B's. And everyone else, I don't know what you're doing. All right. 5. 1 turn, 2 turns, 3 turns, 4 turns, 5. A fifth degree should end like opposite. Like, the ends are opposite of each other. Odd degrees always end that way. And the reason it ends this way is because as I plug in big numbers, the negative starts taking over. I mean, just think about input, output. When I plug in like a million for x, a million to the fifth times -2 dominates the rest of this. So you have a negative output, and it's a huge negative output. So that's why this is guaranteed. So limit of f of x as x goes to infinity, the bigger the number I plug in, that negative dominates. And then the bigger negative I plug in, a negative to the fifth is a negative, times a negative is a positive. You get a huge positive output. So input output could also work for this, or just memorize the action of the graph. And then this ain't no thing, chicken wings. All right. So as x gets huge, negative, y takes off to positive infinity. That's that last limit, like showing my actions, x finger, y finger. Okay, now, I'm not going to do, they asked me like to fill in boxes. I'm just going to, well, never mind, speaking out loud. So what's the minimum degree for this? It could be bigger than this, but what is it? Could it be 2? Yes or no? 3, 2, 1, go. Heck no. Could it be 3? Yes. It could be 3, 5, 7, or 9. Actually, you don't know it. So in this kind of question, actually, it's even or odd. Sorry, it's odd because it could be bigger than this. Sometimes, this could be x to the fifth, and you just don't see one of the. There's not enough more stuff in the equation to make more of the loops happen. So we're talking about minimums. And then what's the leading coefficient, positive or negative? Well, to end like this, the leading coefficient must be what, everybody? 3, 2, 1, go. Positive, and that's all they're asking. So next one, even or odd degree. 3, 2, 1, go. Even. Leading coefficient, positive or negative? Positive. It's just this action, understanding the end behaviors and then being able to do the limits. For this one, limit as x approaches infinity, infinity. As x approaches negative infinity, also infinity. All right, that's how you do those limits. Last one, even or odd? Odd. Positive or negative, leading coefficient. 3, 2, 1, go. It's a negative leading coefficient because look how it ends to the right. As I plug in big X's, Y goes down to that. All right, so what are we on? Page 3? I love page 3 and 4. They are synonymous. We actually break down some thoughts about this, then we actually graph. And that's ultimately what we're going to get to. So my original plan, this kind of leaks over a couple days, but I'm happy about it. I like how it really solidifies a whole bunch of stuff. And I just worked with someone in tutoring on this because, we were just thinking, we had nothing else to do, so I gave him this sheet. He's in my 7th hour, so I gave him, some of the notes here. So what I really want to do, though, is first think about this if I FOIL this. And I guess I have to break this down because we weren't too good on my first question for that. You do realize that this is this. And then ultimately, we know that we're going to end up having to do this. But I'm not going to write it all out. Tell me what x times x is. What is that? 3, 2, 1, go. X squared. And then you're going to have a middle term, and then some other stuff, and then you're going to have to multiply by this. Why am I ignoring the other stuff? I'm looking for the leading coefficient. The next thing I would have to do is distribute this. What's x squared times x? 1x cubed, and then there'd be a whole bunch of other stuff, and there would be no other cube-like terms. That is the top dog. So that's what you need to visualize as happening for me to ask you, what is the degree? So what is the degree of number 5? 3. And actually, quite literally, what is the leading coefficient? What number is it specifically? 1. Because it's x times x times x, ultimately what you would have to do if you were going to multiply this out. So it is a leading coefficient of 1. Now look at what they do. What does this compare with completely? Well, which of the 3? First, second, third, or fourth? It is actually the what one? The third one. So what's the end behavior? We're not going to do that, like choosing the boxes. That's kind of confusing. I'm going to go back to this, though. And I'm going to show something here and then show the graph a little bit. So what are the solutions? What number can I plug in for x to make this 0? 3, 2, 1, go. 1. What number can I plug in here? 3, 2, 1, go. 3. So 1 and 3 are the solutions. And you do write them just like that. 1 is a solution, 3 is a solution. But that means you have an x-intercept at 1, 0, and 3, 0. And actually, I'm going to state my multiplicities. And then this is the learning of the day. We try to learn one little thing and then move on. That 1, 0 has multiplicity 2. And we should know that. We should know that. I probably should have put it with here over here. 1 is a 0 with multiplicity 2. What did I just tell you happens with a graph at a multiplicity 2, 0? What does it do? Starts with a B. There's a C in the word. There's an N in the word. We're like playing hangman now. I always feel so alone up here. B-O-U. Can someone say the word at this point? U-N-C. Oh my gosh, I'm gonna go crazy. I'll be right back. No one knows what the word I'm looking for here? B-O-U. You play hangman every day. What if I had a B, an O, a U, an N, and a C? What would be the last letter? E. What is that, everybody? Bounce. All right, it bounces just like this right here. All right, and I showed you this on the calculator right here. All right, so you had y equals x plus 2 squared, and at -2, the graph bounces. This is something you need to lock in. So get ready to say those as a group when I ask that again. Let's go back to this one. Calm down, Mr. Samuelis. All right, so multiplicity 2. Sorry, my bad, dogs. It's right here. Now, actually, this one's just a multiplicity 1. There's nothing special. It just crosses right through. Sorry, that's a 2. That's a 1. 1, 1, 1, 1, 1. All right, so graph at x-axis. It says use box 1. Graph crosses at the x-axis at the x-intercept or touches the x-axis and turns around at the x-axis. Right? That's what I was looking for the word bounce. So I guess what they're saying here, this one's a letter B, whereas this one's a letter A if you look at those bounces or those boxes down there. Now I got too many B words in my mind. Okay? Bounce and, yeah, got it. So we're going to actually graph this next, and then we'll put all that information together. So if you look at page 4, we actually graph that one. And then I'll show you what you're responsible for cutting that down a little bit. All right, they put that 1/12 there. That's for my next question. But if I were going to multiply this and get it all done, I'd have this long polynomial that's x to the what when you're done as the highest. What would the answer to that be? 3, 2, 1, go. 4. We got some people on board for this. But then you know what? You got 1/12 out in front. And then you distribute it. So the degree is 4. What is now the leading coefficient? I just told you the fraction. 3, 2, 1, go. 1/12. But it is positive. So the end behavior is mostly like a squared, meaning it's good. It's going to end like this, up and up. And we'll see that on the next graph. And the next one, I'll do my limits. I'm not going to do my limits now. I'm not going to talk about the end behaviors. Okay, what are the zeros? What's the 0 for this first set of parentheses? 3, 2, 1, go. -2. What's this 0? 3, 2, 1, go. 3. Both of them are multiplicity 2. So both of them are bouncers, which was letter B, right? If we look at the coding down there, right? Is that what it said down for letter B in the boxes, correct? Yeah. All right, it's going to touch the x-axis, but then stay on the same side of the x-axis. It's actually the word should be tangent to the x-axis. That is a nice little math word. And then use box 1, graphs at the x-axis. Oh, I guess that's what we were supposed to put multiplicities here. I got these switched up. Sorry, I'm getting too excited. These are both mult 2s, so go ahead and switch those 2 boxes or, switch them in your head. I can't even do a U. That was not the pen that time. That was Mr. Samuelis's brain. All right. So again, I love the breakdown of this. We can actually hit this pretty quick. Did I see a hand up there? I thought I saw a hand out in this area. Okay, I'm trying to go fast so we can get this done for the others real quick. By the way, if I multiplied this out, this would be x to the what? it would be 1x to the third plus dot, 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 dot. There'll be an x squared, an x, a constant. But the leading top dog would be x times x times x, 1x cubed. So yet again, all the way over here, degree is 3, leading coefficient is 1. We are looking like that for our end behavior, and we'll get that. What are they asking for in this last box? Maximum number of turning points. That we'll work with that later. Not too concerned with that. Now, people screw this up all the time. We always get this one. What's the 0 for this one? 3, 2, 1, go. 3. What's this one? What's this one? Everyone forgets this one. 3, 2, 1, go. Oh, 0. So a 0 is a 0. That sounds redundant. It's not. That is actually an X-intercept and a Y-intercept at the same time. But people miss this one all the time. Make a big note, and I'm glad this worksheet did this, that I stole this off the internet, this note sheet. This is one of the biggest missed identified 0/X-intercepts. Students miss that all the time. And then we're going to add one more thing when we actually go ahead and graph this. All of these are multiplicity 1. So they're M1 all the way down. So they're all A's all the way down if you look at the coding of this worksheet. It's just going to go right through the 0. Nothing special at all. And then maximum number of turning points, it's 2. I'll see that in the graph, how you're supposed to make these sketches on the next page. Okay? And then I do want to close it because I think that's what I put in our book work. I might extend the video and you can stop if you're at in the 7th hour, but I might open up the book and show you why you should not touch your calculator at all. It should not be needed, I mean. Oh no, I should actually add X-intercepts, but look what they added. Maybe I'll put it in additional points. And the only thing I'm going to do is find the X-intercepts. So X-ints, and then what did we say they were? For that first set of parentheses, it's what? What's the X-intercept? 1, 0. And then I graph that. And then what's the other X-intercept? What do I get for x minus 3? What? 3, 0. Okay, they're kind of squeezed together there. How do I find a Y-intercept? You always plug in what? Who for what? Let's see if anyone can share. 0 for who? Nice. Now, that's something you do have to kind of evaluate. So, P of X is the same thing as Y. But really what I'm finding is P of 0. And it is not that hard. 0 minus 1 squared is negative 1 squared. What's negative 1 squared? 1, somebody whispered. And then this is negative 3. So I get 0 for X, negative 3 for Y. And then that tells me a few things about this graph. Okay, now, here's what you should do. Notice what we did on the previous page. We asked ourselves, what is this when we go ahead and FOIL it out? And it's a 1x to the third. So in the future, when we're just told to graph this, we do this and then we do our thought process. How is this supposed to look? Is it, look at me, is it A, B, C, or D? Which one is it? It's A. So we do that. We say, okay, it's supposed to look like this. And I do this every question that's in this intercept form is what it's called. And now I put everything together. Oh, by the way, who has a multiplicity 2 as a 0? 1 or 3? Which one is it? Well, I'm writing it, so who has multiplicity 2, everybody? 1, 0. What does the graph do at that 0? It's the B word that I went nuts trying to play hangman. 3, 2, 1, go. Bounce. So look at the Y-intercept and then put the end behavior together. This should go through the Y-intercept and forever down because that's how it ends. This should come up to this 0 and bounce. And then I don't care how low the loops go. You don't have to go very low. It's not about that. It's about making the sketch to match the X and Y intercepts. All right? And the Y-intercept certainly makes this graph make sense. Now, I could draw, I didn't do this on the previous page, but the limits are pretty simple. The limit of f of x as x approaches infinity What's the answer to that for everybody? 3, 2, 1, go. Infinity. Where the heck were you? This is so sad. As I plug in a big X, a big Y happens. As I plug in a big negative X, a big negative Y happens. So the other limit is as I plug in negative infinity for X, and it's okay to word it that way. That's how they have it worded on this sheet. We just have to have limit notation. So maybe we could squeeze those limits here now that we see the picture and put everything together. Okay, next one. Maybe before I do anything, what did we say this was? This is 1/12 x to the what when we're done multiplying? 3, 2, 1, go. It's already on the previous page. 4. So that means it's a positive, so it should be something like this. This is how things should fit with the arrows ending up and up. Now we're going to go ahead and do not additional points. We're just going to do X-Ints. What's this X-Intercept? 3, 2, 1, go. -2, comma 0. It's the zeros of those parentheses. What's the next intercept? 3, 2, 1, go. 3, comma 0. Both are mult 2s. Mult 2, mult 2. Let's find that annoying Y-intercept, though. This one is a little bit of an annoyance. 0 plus 2 squared. 0 minus 3 squared. Oh, it's going to be a big number. So I end up with, you might go to the calculator. You know how I do know calculator sometimes. Oh, this actually isn't that bad. Because 4/12 is 1/3. 1/3 of 9 is 3. Nice. Is that too fast? All right. So 0 plus 2 squared is 4. 0 minus 3 is -3 squared, which is 9. 1/12 of 4 is 1/3. 1/3 of 9 is 3. So the Y-intercept is 0, 3. Now I put all my stuff in. -2, 0. 0, 3. 3, 0. And then the fact that this is multiplicity 2 and this has to end up and up, my graph must come from here. Bounce. This doesn't necessarily have to be the high point, but it is the Y-intercept. Bounce and then up forever, and then there's that end behavior that matches what should have happened. Very, very simple. You just have a couple things to remember about multiplicity 2 zeros and how they bounce. This is all we're asking. Okay, hold off for a second and then go to the last one here. Now I think I'll leave it at that and open up the book and just see what we got going on with that. Okay, so real quick, we already talked about the X-intercepts. 0, 0, 3, 0, -2, 0. Do not forget about that 0, 0. It's the biggest mistake people make. Next thing, if I were to multiply this out, it would be 1x to the third, which means it should look like this when I'm done. Right? I didn't even do the limits on the last one because I think the point is made. You should know how to do the end behavior limits after seeing a couple examples. You shouldn't have to keep seeing it over and over and over again. By the way, the Y-intercept is really not that bad. Boy, P of seems to be a popular thing there. Well, that's funny. We already have the Y-intercept because 0, 0 is both a Y and an X-intercept. And by the way, this equals 0 when I plug in 0 for X. So it doesn't really matter. The Y-intercept is the same as the 0, 0 X-intercept. It's not two separate points happening in two different occasions. Okay, so then how do I graph this and how high and how low do I go? It doesn't matter. What you got to make sure you fit, though, is that after this 0 goes down, then we got a little hump here and one here, and then you just got to turn around so they catch it in a smooth curve, and then there's that end behavior I expected fitting the zeros. None of these zeros were special. They were all multiplicity 1. Multiplicity 1s shoot right through. Let's add one more, though, because I just realized I didn't do an x cubed. So let's do this. P of x again, I guess. P of x equals, let's do another x. Let's do x minus 3 cubed. Let's do x plus 4 squared. So ultimately, this is what I want you to do if you don't have it nicely sectioned out. First thing is find the x-intercepts. What's the x-intercept for this? Don't screw that up. What do we end up getting for that? I see those two talking in the back again. Nice. What's the next? 0, 3, 2, 1, go. And then the last one. Okay, and then I keep doing this where it's not very special. If I were to multiply this out, this would be x to the what power? What power would that be? You should be getting this fast now. Go ahead and say it again. 6. You'd have x times x times x times x times x times x. That's x to the 6. What would the leading coefficient be as well? 1x times 1x times 1x times 1x times 1x times 1x. What's the leading coefficient? 1. So this is a positive 6 power. You could have a bunch of terms in the middle. I don't care how many. You're guaranteed to end like this. It's going to end up and up. All right? And that's what we're getting out of that first page. So actually, I'm done. I'm not even going to find the y-intercept. I'm going to go ahead and make a sketch out of this right now. Here's 0, 0. Here's 3, 0. Here's negative 4, 0. And this ultimately is the big connection for all of this. Sorry, I didn't graph that. First of all, negative 4, 0 is a mult2. My graph is going to run through this. Maybe I'll be a cowboy. Yeehaw. Okay. Ooh, that was weird. I didn't expect that to happen. All right, and then this. Oh, that's all right. This is a mult3. And then this is just mult1, which we never write that, but it is a mult1 that just crosses through. So negative 4, what does the graph do at that? Starts with a B, say it, 3, 2, 1, go. And it's got to come from up here because of this, because it's got to end up. So I know starting here, that's where it has to come from, and that's what's going to happen. What's 0, 0? Nothing special. So it goes right through. And I guarantee you, when you go to the graphing calculator, this hump is off the screen. It's like, pew, because, the powers are so large. But you don't have to care about that. All you're doing is making a sketch with this. Why I stopped, though, is this last one, you must do this. This one I'm going to come from below, and then I'm going to come from here and then flatten it out. And then that shows what mult3 should look like. It should look like a cubic function. It should look like the family of cubics, those that know what that is. And that has to be shown. That's your responsibility on that end. So I noticed our 3 examples, none of them had a cubic 0 or a multiplicity 3. So end behavior, and then polynomials, expectations of picture, just from a couple things there. All right, you could stop listening. I stopped listening 20 minutes ago. All right, that's some people. I'm going to go to, the book's on the calendar, right? I just wanted to show you a couple things why the book is a liar. You don't even have to use your calculator, right? So it goes a little extended here, but showing you how you can go on Google Classroom and find the book. And then we're into 3 for this, I believe. Starting up. You guys have the assignment, right? Wasn't it like, this is 2-1, right? Sorry. This is kind of annoying. Sorry that you have to go through all the pages. Look at all the wording in this stuff. Hey, look at the planets. Wow, that's cool. I like that. 2-2. We skipped 2-2. Don't go to 2-2. This is a thrilling video. Teacher going through a book. Nice. There's all the end behavior that they describe. Blah, blah, blah. Modeling. Okay, finally got to it. Okay, 9, 10, 11, 12 is just the matching. You should be able to match those super fast just by end behavior. If I have a positive or negative, x to the 4th or x squared. Very simple. The really ones that I want you to not use the graphing calculator are those. That's what I just did. You should be able to find the x-intercepts. You don't even have to worry probably so much about the y-intercept. I don't know if I did do a couple of these or not. Hopefully it's fine. But look at 17 and 18 and 21 and 22. That's just like what I went through, knowing what the x-intercepts are and then knowing the end behavior. Look at this 22. This would be x times x times x times 2x. So the leading coefficient would be 2, and it ended up being x to the what power? 3, 2, 1, go. 4. Okay, I think a few people are only listening at this point. All right, so x times x times x times 2x would be 2x to the 4th. It would end like this, up and up, and then you'd be able to make a sketch of it. You don't need a graphing calculator for that. You don't need a graphing calculator to determine what the end behaviors of this. Looking at number 28, what is the degree of this polynomial in 28? And I think some people aren't listening at this point. I'm just going to go ahead and answer. It's 4. What's the leading coefficient? -1. So it's down and down. That's how it's going to end. You don't need a graphing calculator for that. Super fast how that happens. So just, don't use the graphing calculator where it says pretty sure. Okay, I'll end at that. Hopefully